Okay.
By
Yeah.
Mizuno. Okay.
Yeah. So the okay. So this is the today's talk about for the numerical method for the solving MHD, but still we are consider about for the mostly the Newtonian MHD case, and then we say the more general way to how to solving for the hyperbolic equation. So this is one of the partial differential equation system. And then yes, so the first I need to say that I've already uploaded for my lecture note to the tomorrow part into my website. So maybe if you can see about for the website, maybe you can download it for the PDF and the keynote version of my lecture note yesterday's one.
Oh, by the way,
Yeah.
can I ask to the
Yes.
students, because I forwarded the information, does everybody receive the information, the link?
Okay.
The site?
Good. Yeah. So this is the recap for that tomorrow yesterday's talk. So this is the conservation form of the ideal MHD equation. Again, this is the mass conservation and momentum conservation and energy conservation and induction equation, and this is the closing using for the equation state. So here, still I can neglecting for the gravitation form. So every source term is just 0. So we are rewriting for this equation to this is more mathematically to handle for this numerical technique. So here, our equation is everything we can see about here, but everything is written to the hyperbolic system. So this is the partial differential equation. So in the general, we can write in for the equation to here like this. So that this is partial derivative of the t is the time derivative with the u. U is, we say, this is the conserved variables. And then partial derivative of the j. This is the spatial derivative part. And then equally for the f. F is, we say, numerical flux and equal to 0. So now we say this is without source. But in more general way, we can add to the source term to s to here. So conserved variable, so compared to this is the previous one, this is the conserved variable including for the 1, 2, 3. This is 4 component. This is the density. This is the momentum, and this is the total energy and magnetic field. Flux is also a catcher for each component for the density part, momentum flux, and then energy flux, and then V cross P term is coming to there. The source term, I couldn't write in for here, it's specified, but usually this is contribution of the gravity or radiation or resistivity or something coupled with that there. So we are solving for this equation, and but this is solving the equation in 4 dimensions, so including for the 1 time with the 3 space time. But we consider each spatial direction separately. Later I can talk about for a little bit. This is the method of the lines, we say. And then here we mostly focus on the 1 spatial direction, so only for the t and x. Yes? Okay.
I'm sorry, if you add some terms in the source,
Mm -hmm.
do you have to implement them also in the energy conservation term?
No, this is depend on the case. So usually we are, if like this gravity just only affect only for the source term, doesn't affect with any energy term. But this is like this radiation. Radiation is also including for the momentum term and the energy flux term and source term also something. This is the case by case equation, but now it's just most simplest situation. Okay. So this is the final differential scheme. So the final differential scheme is that partial differential equation are commonly solved numerically by approximating the derivative with the different operators. So this is a key case. The scheme of these different orders can be obtained depending on the truncation of the corresponding Taylor series for these derivatives. So final differential scheme are based on this discretized of the x and the t plane with the mesh is the discretized point. This is the t equal n. N equal to the different time level. J is a different the grid point, the spatial point, we say. So this is xj equal to the j minus half delta t. So tn equal n plus delta t. So j equal to 1, 2, 3 something. The number is come up. So this is the initial setup today. So where delta t and delta x stand for the cell width and the time step. This is a schematic picture to here. So this circle point is that this is, we say this is a grid point. So here is a j, j plus 1, j plus 2. This is here j minus 1, j minus 2. And then this is one time step. So t equal n time. And then if time is updated, this is t equal n1, n plus 1 level. And then we also sometimes talk about for the, this is cell-centered point. And cell boundary point is, or cell interface point is, we say this is j plus half or j plus j minus half point. So this is a okay, cell-centered. This is conserved quantity usually put onto this point. Then after that, we maybe also say about calculate for to the numerical flux at this cell interface point.
Are you considering that the flow is lamellar, always a lamellar flow?
Mm-hmm.
But this flow is stationary, or it may have
No.
expansion?
This is a depend on the case. After that, I can talk about for to the, this is a linear system or nonlinear system. But hydrodynamics is a fully nonlinear system. So this is each different point. It have to the different information to the to the wave. So this is also affected to the next time step. This is everything correction of
This
the.
is general. You are dividing your system in
Yep.
cells, right?
So this is a, yes.
One-dimensional cells.
Of course, the hydrodynamics, everything is smooth, a continuous flow. But numerically, it cannot handle for the discontinuous case. So the one case we are using for the finite difference, it means that everything discretized as a point to point. Then we can update it for the disposition to there. So the finite difference is now first let's consider the following scalar PDE. This is the most simplest situation. So this is u is the time plus the f is function of the x, and then u equal to the x0 point, and then f is just only function of the u. So the finite difference scheme is for this equation. It's time marching is proceed to obtain the approximate to the solution in the mesh point u j n plus 1 point from the approximated the previous time step u j the 1 point there. So we need information to get in for the next time step point. We can collecting up to the some information from the previous time. So we can approximate the time derivative with this first order forward Euler difference, and this is a special derivative with the first order central difference. So here, so ut is divided the n plus 1. This is the next time step minus current time divided the delta t. This is the difference of the time, and the space point this is j plus 1 and j minus 1 is the same the t equal n point, and divided by 2 over delta t. This is the central difference between each discrete point. Then we can catch the combine together. It's including for this equation. So we can get in for this kind of equation. This is we say explicit first order central scheme. So this is u j point n plus 1. This is the next time step. It's calculate for the u. It's j point plus the previous time n minus. So the delta t over to the 2 delta x, which is this is f. This is j plus 1 minus j minus 1 is the previous time. So this is some correction. This is the same point with this one. And then how much correction is come up to here? It's getting for this different next grid point to how much flux is inside, how much flux is going out. Then we can estimate to the next time step value into there. So this is the most simplest calculation to this finite difference. Okay, so that this is many order first order and higher order approximation are available in the literature, but this is the most simplest situation. Okay. So this is the method line. So the generic name of this family of the discretized method in which this space and time is the variable deal with separately. So this is also same as the 3+1 approach. So time and space is discretized, or separately we can approach over there. So time is discretized with a finite difference, and space discretized is done into the various way. using for the finite difference or finite element or spectral method or some other things. So the method line is completely considerable for the time evolution part onto the this is spatial derivative part is separately. So we can apply to the any kind of the method is mixed up to the calculation. So this is Hydrodynamic equation can be written in the compact way as a this is semi-discretized system. So this is a time derivative of the conserved variable u. It's equal to just s. So this is s is remaining term into the evolution equation, including for the spatial derivative plus source term part. So if see about for this equation, so this is looks like a PDE. It's changing for the order differential equation. So this is standard ODE integrator can be applicable. So this is first order forward in time is the Euler step. It's using for the u n plus 1. The next time step is calculate for the u n plus the delta t times the this s. S is also here to calculate for the previous time with the this is including for the conserved variable inside of the previous time. So second order Runge-Kutta scheme is we can put onto the one step into the between to the next time step. You writing for the u star. So calculate for the next time step using for the contribution of the previous one plus this is half time step part, and this is calculation of this flux correction part also there. So higher order in the time it's including for the this is second order Runge-Kutta, third order, fourth order, fifth order. This is increase everything down, but including for the Runge-Kutta scheme order, it means that we need additional half time step. So this is the many scheme also available into the time. Yes.
So how was calculated S star?
S star is using for the we can calculate for the U star. This is half time step. Half time step you can update it for the all primitive variables and also calculate for the numerical flux. Then we can update it for the S star. Okay. So this is also method line. It can be used with any spatial discrete method, but this is a finite difference method. It's a finite difference scheme is a fairly standard choice using for the method line because both cases there. So this is the field value at the grid point are represented by the array. So this is we say this is uijk. This is a three-dimensional point, and then so this is u is including for t and xi, yj, and zk. So this is a three-dimensional point over there. So the spatial derivative is making for the like this the spatial derivative of x is u. It's getting for the ui plus minus ui minus 1 divided to the delta x. If making for the second derivative of the u, we can get in for the ui plus ui minus using for the uij point. And this is delta x is square. So this is second order derivative. If this is mixed up for the x and y derivative, especially, we can also calculate for the this is discrete point x and this I plus j plus or I minus j plus. This is mixed up to be so there. So any kind of this kind of spatial derivatives you can calculate using for this discretized point. So we say this is a stencil. This is a set of the grid point need to discretize space derivative at a given point P. Then this is also provide a numerical domain of the dependence of the select point at any perturbation at one stencil point. So we'll change to the computed value at a P after the single time step. Then this is the numerical propagation speed. We can calculate sometimes. So this is delta x side over to the delta e. This is s is the stencil side. So this is the final difference. Every time we need some information, it's neighbors, how to change in for the one point to calculate. So there. Okay, so this is physically, for this system is describing the wave propagation with some characteristic speed. So you know that this is wave is just propagate at this speed. So that this is the field value at the P, this is causally determined by the value inside the past the half cone with the vertex at the P. So now we have schematic picture to here. So this is the next the time step, t equal n plus 1 time. This is the previous time step, t equal n plus 1. So here we want to get in for the updated for information, this p point. But this p point is coming from this information for the j minus j plus. But this is the causal point. It's just only to inside here. In this case, this is causally out of the information is here, but this is unphysical situation. So we are every time think about what's the causal information is coming to here. Then this information j minus 1, j plus 1, it should be inside in this causal information.
So the great triangle is the light cone.
Yeah, this is the light cone, yes.
Okay.
Yep.
Oh, sorry, the light cone here?
No, this is not right. This is the propagation of the characteristic speed information. So yes, not the right way. Of course, in the GR, yes, relativity think about for the light cone, but this is the pure wave propagation.
Like sound wave, for instance.
Yes.
It's the propagation. Yes, it's similar to light cone, but it's for the wave, for instance, a sound.
Yeah.
Sound speed.
If you think about for the hydrodynamics, so this is sound speed. It's this kind of information.
It's the fluid cone.
Yeah, fluid. Okay, yes. You know, characteristic cone we say, or causality is something we can say, right?
It's not at the fluid velocity, but at the wave, at the sound speed or Alfvén speed.
Yeah.
It's magnetized.
But in the relativistic case, will be the light cone or not? Because the sound speed will be the characteristic velocity of the system and probably
Yeah.
will be the
Yeah, of course, in a relativistic case, we can sometimes using for the light speed. It's some, of course, it's the information for the causal information. But after that, I can talk about for the HL or HLD or some other approximately Riemann solver type. This need also using for the wave speed information. Sometimes we can using for the light speed. This is the most simplest way. But this is getting for the little bit diffuser structure to compare to the exact wave speed. Of course, this is information. It's something. Of course, all physical information is propagated out to the wave. Like this is the fast magnetosonic wave over the sound speed. But if you think about for the light speed, this is the only maximum point we can consider about there. So this is something unphysical situation. But this is very minor if you think about the fully relativistic situation. Okay, so this is the Coulomb the condition for the numerical stability. The physical domain of the dependence of P must be included in the numerical domain of the dependence to here. So this is provide the upper limit of the numerical time step to here. If you think about for delta t is too much large, if this is case is we lost the some connection or the causality, then the system or solving equation becomes unstable. Then we can solve about for some unstable behavior of the simulation. So this is some information because we are discretized up to the time dependence the simulation to indicate. So we need some minimum. Yeah, this is we say this is an upper limit to delta t to calculate for the next time step. Okay, so this is the characteristic. So the hydrodynamic equation involving for the wave propagation, because this is a hyperbolic equation we can solve. So this is remember they can be written into the first order a quadrilinear form to the equation. So here we can write in for to the partial derivative t equal u plus a times to the this is a spatial derivative x is the u equal to 0. So here a equal to the function of the u. This is the partial derivative f over partial derivative u. We say this is Jacobian a matrix. If this is the Jacobian matrix has a constant coefficient, so it means to the linear case, the solution produces a simple. So that this is first we diagonalize the Jacobian matrix so that this is making for to the delta. So this is using for the Asian vector matrix, and then this is the Asian value matrix is getting to here. Then this could include for to the all this is lambda information. So if we define this characteristic variable using for to the w, this is it's r minus 1 times u. So we can decompose this original system of the equation to like this. Then this is of course we can write into here. So this kind of information is characteristic variable are also constant along to the curve of the x and t plane. This slope is corresponding to the Asian value there. So we are just information about this characteristic speed. So we try to see about for this picture to here. We can schematic picture now it's written to here. So such a curve is called the characteristic curve. The slope is given by the local by the characteristic speed. So here we are think about this is the space and this is time. This is t equals 0. We have this is wave, and then this is next time step. We can see this kind of the feature. But there.
Excuse me.
Yeah.
Is this clear to everybody, even those that are who are not familiar with the numerical? Okay, is this clear? Because when he enters in the relativistic approach, these characteristics will be more complicated. We are not going to have exact solutions. So this is the chance for you to ask questions. Okay.
Just a small
Yeah.
when you talk in hyperbolic equation,
Mhm.
for instance, in the relativistic framework,
Mhm.
we are in general worried about causality.
Mhm.
But it seems to me that in this context here,
Yeah.
hyperbolic equation has nothing to do
Mhm.
with causality.
This is causality we are every time consider about for this is if you think about for this finite differential scheme, we can get in for the delta t information. So this is completely follow to the causality information. So what kind of information you can catch if you can within yeah. So if you if you can not follow to this causality situation, this using for this numerical method becomes unstable. Then simulation structure or result is completely different structure to show about. So at this causality is one of the most key issue inside to numerically solving for this finite difference model. Even for the Newtonian case, we don't worry about for any light cone or light speed causality, but all information is propagate at the wave speed. So this is the characteristic speed inside here. So we need to treat this one carefully. So no, not clear.
No, this is standard. I know this is standard knowledge for people that work with partial differential equations. It's just a method.
Yep.
It's just that I'm not used to it.
Yep.
And I saw this before when we studied the Riemann problem, but
Yep.
now I like okay. No, but it's so.
Yeah.
So can you elaborate on the meaning of the dash lines there?
Yes. Okay. So dash line is meaning of we are writing for the characteristic speed as a different as a characteristic curve may focus on something. So because of that, after that I can show about for the two example. One is the advection equation. This is a linear wave propagation equation. And then next one is we can show about a nonlinear wave equation. This is a Wager equation. How much changing for this kind of characteristic propagation, and then how much affect this structure. Maybe later a little bit talk about this one. So important point, we can get in for the characteristic speed, each point of the wave information over there, this discretized x point. But this characteristic curve to this characteristic speed is different position to position. Then this information is collecting for the next time step as a profile of this wave, how to propagate over there.
It's related to the sound speed.
Yes, that's right.
If it's hydrodynamic.
Yeah, this yes.
The signal propagation speed.
Yep. This is signal propagation speed. Yes, this is correct one. Of course, it is hydrodynamics of the MHD case. We have several different waves, but this fastest one is the fast magnetosonic wave. Or if you're solving about for the Einstein equation also solving about for some propagation up to the space time. This is also the information propagate out to the light speed.
Causality here
Yeah.
has only the Newtonian sense.
Yeah.
If you know the initial value and then you may propagate.
That's right. Yes. This is a Cauchy problem. So this is an initial value problem. Yes.
And the slopes of the characteristics
Yeah.
are smaller where the speed is bigger.
Mm-hmm.
So
Yes.
what distinguishes a characteristic in your plot?
Yeah.
this slope and a
Yeah.
characteristic with this slope.
Mhm.
What's the difference between these characteristics, the slope?
This is the speed. So this is
Speed.
this is the x and t, right? So this is opposite. Yes. This is just the speed.
Just
You can.
like a space-time diagram.
Yep.
Okay.
That's right. So since they constant along to the characteristics, so the value of the characteristic variables at any given time known at once, initial value is known. So this is the initial value problem. I just mentioned today.
I will sit here with my graduate students
Okay.
and chat with them.
Yeah. Okay. So this is the one of the initial value problem. So if you get info to the any point of the x and t, we can get info this information to the propagation to the each point of there. Okay. So once the solution is known to the in terms of the characteristic variable, so it is straightforward to obtain the solution in terms of the original state vector. So using for the w is this is r minus 1. Using for the this is u is also r times the w. So we can everything to get info to the now this is a one-dimensional propagation, but this is also all point we can get info to this information. So if we know about for this characteristic speed, then we can get info to the all point information. So the solution is a linear superposition of the nth waves. So we are sometimes characteristic is coming for the one direction, and then this is also catching each other. So the each point is a combination of the different point of information over there. Then this is each propagation is independently the rest with the speed given by the corresponding eigenvalue of the Jacobian matrix of the system. Then this so-called Godon-type method, this is extended to this concept to the nonlinear hyperbolic equation. Especially we need to solving for this Hydro and the MHD. This solving for the Riemann problem of the new system of the equation. This is obtained by the writing the original system as a quasi-linear system. And this is the spectral information of the Jacobian matrix. Also is based on the such solver for the linear system. So later I can touching with this Riemann problem also to how to get info this one. Okay, so first before to discuss with the solution of the hydrodynamic equations, so there are also aspects that they are the nonlinear nature to the point of out. So first we are showing about for the most simplest linear hyperbolic equation. This is the advection equation. So advection equation is here. So the partial derivative t is using for the u. You have a x, and then the spatial derivative x is including for the only u to here. So this is the solution is initially once is very simple translated to space and time. So because this is the propagation speed is everything constant in the everywhere. So if you see about for the characteristic line, this is the space and time. This is the initial point value, and everything is parallel to here. So this is just advect to the information to there. Okay, so this is the linear nature of the equation of this advection equation. Okay, so next is the most simplest is nonlinear hyperbolic equation in the Berger's equation, we say. So this is just differences here. So this is the time derivative u plus u times spatial derivative xu. So this is the important part is this u is included here. Because this is right hand side is 0 in the inhibited limit. And then despite the similarity with this advection equation, its solution is much difference to here. So here I the schematic picture to here. This is the last time same. This is a simple sinusoidal propagation the wave. Initially we can set up, but the characteristic is speed is different to the point to point because this is dependent on the u. Then this is making for the some changing or shape of the waves. So here is one of the simulation we can show about for the time difference, time evolution of this system. So we are see about for this here, but this is catch up for the wave. Then making for this kind of the discontinuity. We say it's shock it's making up there.
Excuse me, what is
Yeah.
over there? What is the, yes,
This is the u. This is the u value with the x point, and then this is line, different line is getting for the different time.
u versus x?
X, yes, this is spatial position, and this is the u value. There. Okay. So Yes. So this kind of the behavior is known as a shock steepening. Yep.
So I remember vaguely this from reading Toto's book.
Hmm?
So
Yeah.
the value of u
Yes.
is constant along a characteristic curve, right?
Hmm?
Okay.
Yeah. So because yes, this is just only function of u. It's u equals just only getting for the points of it here.
Yeah.
So this is everything is constant here. So and then it's a consequence of this propagation speed not being the constant. This is the position to position different. Then this is contrasted to what happened with the advection equation, but as a function of the speed and time. Sorry, this is not constant. This is also function of the time. Okay, u is. Characteristic speed is getting for the u, but this is also position to x and then also the function of the time. Because u is changing for the next time, this is the value become, so some cases the value become faster to catch up for to the one case. This point looks like this. At this point become to the character speed it's very slow. So it doesn't slower. Then another one is faster become faster. Then this is catch up for the later. Okay. So this is the maxima is the waves move faster than to the minimum is tend to the reach of them. And then this is the propagation up to the equation, not in the initial data. So even smooth initial data, we will lead to the approach to the shock in the after the time into the case of the invited fluid case. So this is the one of the simulation I can show about here. So this is the Bagger's equation to solve into here. Then initial value is just only constant for the sinusoidal the profile over there. So if you see about for here, this is sharpness starting from there. Then this is keeping for to the shock wave structure. But this is also some dissipation is also happen to later times.
Can you give a simple physical application of the Berger's equation? I cannot remember a simple system where it is relevant.
Internal shocks along stellar jets, for instance,
Mm-hmm.
not stellar, young stellar objects. The internal shocks, they do behave
Okay.
like the Berger's equation. This was
Mm-hmm.
demonstrated in the
But
90s.
I think it's a normal hydrodynamic equation. This is a completely nonlinear behavior. So nonlinearity is important. This is the most simplest nonlinearity we can put on there. So any kind of the nonlinear hyperbolic equation show about such kind of the difference. So like this is shock steepening or something.
Nevertheless, you had this term on the right hand side.
Yeah.
And
So this you say this is the dissipation you mentioned?
Yeah.
Okay, yeah. Mm-hmm. Okay, something, yeah.
He's
Said
mentioning.
that the
Astrophysical
Berger
equation.
equation appeared in cosmology,
Mm-hmm.
and you are out of the linear approximation
Yeah.
to the galaxy formation
Mm-hmm.
process, and then one of a basic equation is the Berger equation.
Yeah. Thank you. Okay, so this is the high resolution method. So the high resolution method is modified to the higher order finite differential method with the appropriate amount of numerical dissipation in the vicinity of the discontinuity. So the quantity u is this n plus j is approximate using for the u x j plus t equal n. But in case of the conservation law, it is preferable to the view it's approximate to the average within the numerical cell, x and j half and to the x the j plus half. So we have think about for the previously discrete is the point is a cell-centered value, but we have must think about for this value it's cell averaged value. Cell average is getting for the this is between to the this is each discrete point. We say this is j plus half or j minus half. And then this is divided by delta t, it's getting to here. So this is integrated value. Okay? So this is constant with the integration form of this is conservation law. For the hyperbolic system of the conservation law, the scheme between the conservation form is guaranteed that its convergence is to one of the so-called weak solution of the original system of the equation. So this is a important point. We need getting for some convergence to this is the conserved equation. So we are guaranteed to get info to the how energy is conserved into the, or some momentum is conserved within the simulation. So scheme is written in the conserved form. It's read to here. So this is the u, the j point plus n plus 1. The updated time step, it's getting for to the u j n times minus delta x over delta t. Calculate for the, this is the f hat n j plus half or j minus half. Here, this is f hat is a numerical flux function. So it means to the j point, this is the cell, one of the cell. Then we can consider about for the j plus half or j minus half. This is the left-hand side, right-hand side of the cell interface. How much flux is including or go out with this cell. Then this is getting for to the next time step information. So higher resolution method, it's important point is how to get in for this kind of numerical flux. This is our now it's modern technique to include in here. Yeah.
Simple question
Okay.
to the Burger's equation.
Okay. Yep.
If I remember, I think the eigenvalues of the matrix
Mhm.
form of the Burger equation
Yep.
correspond to two eigenvalues, plus
Mhm.
and minus
Now.
the characteristic velocity.
Mhm.
And when you show the evolution of
Mhm.
the time evolution of the Burger equations, how it's possible to see this velocities? Because if I understood, it's possible to see just the shock
Yes,
function,
steepening,
the
yes.
wave that's
Mhm.
propagating from the left to the right, and
Mhm.
and the second one that corresponds to the wave propagation in the opposite direction.
How to say?
This is a point you see only the discontinuity.
Yeah,
I remember, but I'm sure it's
yeah, this is two.
eigenvalues.
Yes, I think it's a two eigenvalue. It's just going to about for the right direction or left. I think the shock wave is everything is going right direction. And then this is only for the one direction over there. Of course, we are both information is propagated right and the left hand side, and this is correction is come to there. But steepening is happen to this one. Everything is both. I think it's going to the right direction. As far as I remember. Yeah, maybe I need to check later. Yes. Okay, so this is the numerical flux. So this is the conservative form. So the conservative form of the scheme is ensured by the starting with the integration version to the PDE in the conservative form. By integrating with the PDE within to the space-time the computation cell. So here we can already think about the average of the cell. This is the cell interface and time to the average up to the time with the delta t is delta t1. So the numerical flux function is approximate to the time average flux across the interface. Yeah.
Average over time.
Yes, average over time, average over the space. So this is that we need both. It's averaged out to there. So of course we have a different time. We need a little bit to change it, but this is we cannot handle it for this one because if you see about for the very small delta t, so we can think about for this is integration of to the all information with the this is flux. It's getting for the next time step. So this is the integration of the flux. This one is already integrated about for to the space, but also including for to some integration of to the time also. So this is the flux integration depend on to the unknown. This is a solution as a numerical interface during the time step. So this is the u value is getting to here. How to calculate for the flux. So this is the key idea. It's the possible procedure is to calculate this solution by the solving for the Riemann problem at every cell interface. So now it's getting for this one. This information getting for the 0 time unto the equal j point and j plus 1 point something. So everything is now it's previously I can talk about for the characteristic. Characteristic information is important to the propagation of the information up to the solving for the waves. So this is hydrodynamics is also same. We need to think about for the what kind of the information is propagated to the next time step. This is we say the Riemann problem to get into here. So Riemann problem is an initial value problem with a discontinuity initial data point. So here this is we can say about for the left and the right if equal x equal going to lower or higher case. this is the solution is constant along with the straight line x over t equal constant. Therefore, it means the self-similar situation we can consider. So it's consistent with the constant state is separated by the rarefaction wave. This is a continuous self-similar solution of the different equation, and also shock wave and the contact discontinuity. So here, this is one of the sample we can show about here. So this is the x equals 0 point. We have a this is a variable here. Left point we have some difference, and then this is discontinuity with the right value to here, UL and UR. If you get in for this value, we say this is the Riemann the solution to add to this point. We can propagation of the contact discontinuity, propagation of the shock wave, right direction, and left direction is propagation to the rarefaction wave. So this kind of information is every time it's happened for the one time to making for some discontinuous structure is made up. Then this kind of separation, current, the contact discontinuity, shock wave, rarefaction wave, this information is every time it's depend on to the initial this discrete setup. So sometimes making for the 2 shock wave, sometimes 2 rarefaction wave, but this is also depend. The incorporation of this exact solution of the Riemann problem is compute a numerical flux in the Euler equation is due to this is Godunov type. Okay, so this is so when the Cauchy problem, so it means the initial value problem is a discretized as a set of the continuous partial differential equation is solved in the discretized form. The numerical solution is a piecewise constant, we can say. So this is the local Riemann problem. We can correction up to this one. So here, this is t equal n. This is one of the solution like this here. But we know only for the value, it's just only for this circle point. Then we are making for this is averaged out here. So we have this kind of the step function structure. It's just only we know the information of there. So this is the discretized simulation case. Of course, this is U value is every time the constant and continuous, but we say this is average out over there. Okay, so this is it's particularly problematic when the solving for the hydrodynamic immediate equation for the compressive fluid. So the hyperbolics is a nonlinear characteristic produced with the discontinuity solution in the finite time. So like this, a shock wave, contact discontinuity, even from the smooth initial data case. So any numerical scheme must be able to handle the discontinuity in the satisfactory way. So the problem for our hydrodynamic equation, every time we have even for the very smooth equation, but this is nonlinearity making for the shock wave sometimes. Then, but this kind of our numerical approach, it's how to handle for such kind of shock wave is quite challenging. It's now. So now we this is a numerical approach. We have to think about for this is 4-way. Now it's here. One case is the first order accurate scheme, like this a Lux-Friedrich scheme. In this case, we see about a non-oscillatory structure based on the shock wave, but this is inaccurate across the discontinuity. We see some diffusion structure to salute this shock wave. Second, we are considered for the standard second order accurate scheme, like this Lux-Friedrich scheme. This scheme shows about for the oscillatory structure across to the discontinuity. This oscillatory structure, of course, this is completely numerical, not physical effect. Third, we are using for the second order accuracy scheme with artificial viscosity to damping for this oscillatory structure to making for the shock. Fourth, we are using for the Godunov type scheme, using for the upwind high resolution shock capitalism scheme to handling for the shock wave and to getting for the higher resolution. So later, most of the current the numerical code using for the finite difference, solving for the conserved form, using for this high resolution shock characteristic scheme to here. So I try to show about for some example for this 1, 2, 3 little bit later here. So this is solving for the linear advection equation. Then this is the top panel show about for the first order scheme is a famous Lux-Friedrich or upwind scheme. So initially we can set up for this blue structure over there. One case is smooth structure, and another one is the discontinuity shock type structure over there. Then after the time the simulation is happened, then this is green is the simulation result. So of course we couldn't see any oscillatory structure, but strongly smear out of this structure. Yep.
Can you just Yosuke, elaborate the solid lines are the expected target solution?
Yes, this is the target solution. Initially we can set up. Then this is completely advection equation. We just keep in for this structure as much as. Yeah. Then this is the second order oscillatory second order scheme, like this Lux-Wendorf scheme or McCormick scheme. This is show about for this is smooth structure. Maybe we can see that this structure a little bit nicer to follow up the initial structure, but shock wave is a bit weird. We see also something follow to the shock type structure, but we see that some undershooting and overshooting to here. We say this kind of structure is oscillatory structure. So Lux-Wendorf scheme is previously we are using for so many times, but this kind of scheme also have some problem around the shock wave structure. Maybe smooth structure is maybe okay, but shock is definitely not using this one.
Which one involves the least amount of arithmetic operations?
Mm-hmm.
Which one would be the fastest, the lax free?
Of course, it's the first order is the most fastest. Of course, this is the first order. Second order needs to be a little bit more expensive, but it's compared to the current hour status the code much simpler.
So the Godunov is the most expensive computationally.
Yeah. That's right.
Lux and Drop.
Yes.
In the past, I mean the 90s.
Yeah.
Those I used
Mm-hmm.
Lux and Drop. But what is the difference between Lux and Drop and
McCormick. I forgot both the second.
yeah,
Both second order the discrete one, but
very similar solutions
yes,
according to
yes.
this interpolation.
Yep.
So do you remember the
sorry, I forgot the this one. Yeah, maybe I can need some textbook. Maybe we can catch them for the difference. But here, most of that is I think in late 90 or something, that early to 20s, they are using for the Lux-Wendorf very frequently, and then they also handling for the next technique to using for the artificial viscosity to handling for this or flux limitation to using for this shock structure. Yep.
We use mostly artificial viscosity
Yep.
in SPH.
Mm-hmm.
Till nowadays, I mean,
Yes.
of course, nowadays there are these mixed
Mm-hmm. Yes.
codes and techniques, but
So this is another show about for the case. This is a Lux-Wendorf scheme, and then this is the second order TBD. The viscosity is including from here. So this is smooth structure is also Lux-Wendorf is good, but this is shock structure is also show about for this oscillatory structure. But if you think about for the TBD, this is total variation diminishing method, or we can put on the additional some artificial viscosity. We say this is TBD viscosity. We can see about for the shock structure, it's very nicely to follow to there. So at this,
This problem is a characteristic of the hydrodynamics.
Yep.
In hydrodynamic, for instance, if you have a perfect fluid
Yep.
and the hydrodynamic equation, and then when you try to integrate,
Yep.
and
Mhm.
this Riemann problem appears.
yes. So I think it's if we think about for the inviscid the fluid situation. In this case, we doesn't have any shock wave is developed. So in this case, everything is a smooth flow. We don't worry about anything so much. But hydrodynamic is nonlinear equation. So this nonlinearity is making for the shock waves. So this is Riemann problem here. So it's a shock is quite hard. So it's if it doesn't have any shock wave, we don't worry about anything so much. But if including for the shock, we have a most of the numerical technique. It's fell down to this way.
Because it has been proved, even analytically,
Mhm.
that when you try to incorporate dissipative process,
Mhm.
in general, maybe in the relativistic case or
Mm.
in the non-relativistic case, there are instabilities.
Yep. Mhm.
Maybe in any formulation that you use, for instance, in relativity, you use the Landau formulation or the
Mhm.
Descartes formulation. Those formulations are unstable
Mhm.
in the sense, but this, if I am understanding, these instabilities
Yeah.
are not in principle related with the Riemann problem.
Mhm.
That's right.
Yeah, this is a completely numerical thing. It's not a physical situation. Because the numerical, our finite difference numerical scheme have the instability at the discontinuity. So this is,
You are dividing your continuous flow in cells, then you have to solve this transport of momentum and everything from one cell to the other, and you may have these discontinuities, so you have to smooth out in order to get a continuous solution.
Okay, it's a problem of the method.
yeah, this is, yes,
Numerics.
this is numerical problem to here. So at this currently, we don't have any perfect numerical method to solving for the both
Unless you integrate.
high resolution to the smooth structure and then getting for the nice sharp the shock structure without any dissipation. So at least this is a CFD, the computational fluid dynamics. Still, we have one of the field to doing for the research there. So we also every time we try to update it for the numerical technique, they propose the new numerical technique. We try to apply to using for the how behavior of our simulation. So this is every time we need updated time to time.
Yuzu,
Yeah.
the upper part you have
Yes.
Laxman drop, and
Yes.
the bottom
Yes, this is TBD. The TBD, that total variation diminishing. This is one of the flux. How to say? Is a constraint, and this is something like this. Is a TBD term. We say additional viscosity, including here. In this case, the TBD is the total variation is diminishing. It means that we don't worry about for any overshooting or undershooting. Everything's smeared out. So this is correction term is counted here, then making for the smooth shock structure. Yeah.
I don't know if this is the moment to ask this, but
Yeah.
I have doubts about the artificial viscosity,
Mhm.
because you will apply this to smooth the discontinuity
Yep.
to make more precise the solution of the
Mhm.
system. But if you get the hydrodynamic equations,
Yep.
this will introduce, this will break the energy conservation.
That's right. Yes.
So
Yep.
my point
But
is
this is
how
on-
much is reliable,
That-
how
yeah.
much is reliable the application of the artificial viscosity.
That's
but
right.
this is on purpose, exactly to get rid of the discontinuities.
Yeah, but
Yeah.
even though this will
So-
break the
Yeah. So of course the early 90s they are using for the discount. Mostly the focus on the how to handle for the shock is nicely. Then they apply for the artificial viscosity. Then later it's gotten of type of the method it's proposed. Then we are concerned about for the what's the conservation of the energy or the momentum within the simulation. Because this is kind of relax-based scheme or some other this TBD or scheme, it's usually solving for the non-conservative form of the equation. Then we doesn't get in for the any non-conservative form. It doesn't guarantee to the conservation of the energy of a simulation. Of course, we can do it for simulation. We can get in for some estimate of how much energy is contained in the simulation, how much energy is going out. We can estimate how much conservation is come, but this is not guaranteed, the simulation. So that we are consider about for the more physically correct situation. So we think about for the more conservation case to there.
The interesting point is that in artificial viscosity, you make it, it's such, I mean, the function that you use is such that you ensure that it's big, the correction is big in the discontinuities because you have this velocity, this shear, right? You get the average, and then regions where the discontinuity is smooth, it is really small because you have no discontinuity. So it does, the correction is really smaller than the numerical error. So
Yeah.
should be fine.
But
At
of
least
course,
in
yeah.
SPH.
Yes. But of course, this artificial viscosity is problem. So the how much viscosity we need put on there.
Yeah.
So this is by hand. And then if you put onto the strong viscosity, we have a strong dissipation that happens there. So this is so much smeared out for this shock structure.
Yeah,
That,
you need to make a lot of tests.
yeah. So this is a hand. Yeah. This is so fine tuning to the simulation. So it's
But after
yeah.
several tests, you know the numbers. You have the right numbers too, and it works.
So yes. Okay. So this is a Riemann problem. So now here, so we have this is now it's one function. I think the pressure to here. So this is the point to here to the different point to here. Then this is j equal point. This is j plus 1. This is j minus 1. This is cell center value, and then this is a cell boundary value. So here we are focused onto this point. Then we need to calculate for this cell boundary value where the flux is requested here. Then this kind of information is getting for here. So we are think about for this is the initial data at t equal n for the two Riemann problem at the cell boundary. This is j plus half or j minus half position. Then here this each cell boundary point we can think about for the Riemann problem. The both of right the information is propagated right hand side, left hand side, or propagation of the contact discontinuity, something like this. Then this is the spatial evolution of the two Riemann problem at the cell boundary. To here, to each problem lead to the shock wave and rarefaction wave moving. This is opposite direction. Then this is solution at the t equal n plus 1 time. This is a two Riemann problem at the cell boundary is getting to here. Then we see about for this kind of solution over there. So this is everything. This is the initial value. Then we can consider for some Riemann problem. Then this is some solution to later to here. So here we see about for the shock wave, the rarefaction, and this is shock wave, the rarefaction. Of course, next time this rarefaction is propagate right direction, and this is rarefaction propagate left direction. This is meet each other. Then also changing to the time structure. So in the Godot scheme, the structure of the Riemann solver, the Riemann solution is lost in the cell average in the process. This is first order in the space. The exact solution of the Riemann problem is computationally very expensive. So particularly into the multi-dimension and for the complicated equation of state case. So now it's mostly we are motivated to developing the approximate or linearize the Riemann solver to case. So that most of our current the numerical code using for the approximation Riemann solver scheme. So based on the exact solution of the Riemann problem, this is corresponding to the new system of the equation is obtained by the linearize of the original one. This is a quadilinear form. The spectral decomposition of the Jacobian matrix is based on the all solvers. This is extended idea of the linearized equation. So this is shown above for the previous one. This is same as A. This is Jacobian matrix. So approach follow to this subset of shock capture scheme. This is so-called Godot type of scheme. So this is standard implementation of the high resolution shock capture scheme. First, we are step by step. I try to say this is time updated part. Time updated we are using for the method of line. So this algorithm is using for the conserved form. So this is a solving equation. To basically here. So this is so this is again here. We can discretize the position to the space. This is now show about j plus 1, j plus 2, or j minus 1, j minus 2. Then time updated next is next t equal n plus 1 time. Also see we can get info the information of this each cell point there. So this is a equation to solving here. U j point plus n plus 1 is calculated from to the original value u j plus n minus so delta x or delta t, getting for the flux information to correcting for the what the flux is coming from between to this cell boundary, cell interface position. Then addition to the source term is evolution with the time. So in practice, the use to second or the third order time accuracy, the conserved Rouquet-Kutta scheme, we can try to use it for the this time updated in the high resolution shock capture scheme. So time evolution, we are writing again. This is a system of the conserved equation. So we are everything is going to the right hand side to the spatial time with the source term correction, writing for the L function of the U. So we using for the multi-step TBD Rouquet-Kutta method for the time advance of the conserved equation. RK2 is the second order, RK3 is the third order in the time. So RK2, RK3 is the first step is similar. We just using for the one time step. RK2 is getting for the two step. But a third order case, we need second step and third step is correction to here. So if you think about for the fourth order, fifth order, you need additional sub-step to calculate to get in for the next time step evolution. So this is a follow to the ordinary equation to know about for the famous Rouquet-Kutta method. Okay, so this is the next is think about for the cell reconstruction. So cell reconstruction, its cell-centered value is that this is a primitive variable to interpolate the right and left hand side of cell interface value to there. Why I need this kind of information we should do? Because after that we need calculate for the flux at the cell interface position. So cell interface, most of the simulation is updated for the cell center value information to here. So we need information, it's interpolated for this information with this cell boundary value. So this kind of the reconstruction, we say the interpolation, we are using for the piecewise constant or linear interpolation like this Mascal flux or the monogenic center flux limitation or fan layer flux or parabolic way. This is a piecewise parabolic method or more higher order interpolation like this Weno or MP or some other things. A procedure to use. This is getting for to the spatial resolution mostly to inside the simulation to there. So this is a very if you get in for the higher order, of course we need more higher stencil information to there to making for the interpolation. Next, we can calculate for the numerical flux. After that, we can reconstruction up to the physical information at the cell center to the cell interface. We are calculating for the numerical flux at the cell interface position from the reconstructed value based on to the Riemann problem. So mostly we are using for the approximated Riemann solver to say about for the rho or HL, HLC or HLD flux are the used. This is expected use for the spectral information of the system. It is used only for the maximum left and right hand side and going to the wave speed into there. So this is a schematic picture. So this is if you get in for the primitive variable information into the cell center. So we need to get in for the cell center value until the flux is calculated. So how much flux is getting for the one direction over there. So just this is using for the lambda r, lambda l. This is a fastest characteristic speed going to the right hand direction or left direction over there. Then the FL, the HL flux is calculated for this kind of the equation. So this is we are simply think about for this three situation. If this is the lambda r equals the larger to here, we think about the only right hand state, or this is left hand here, this is left hand state over there. Or we can mix up this is two intermediate state, we can get in for this between to them there. So this is the flux is calculated for this kind of information. So we know information about for the flux getting for the left hand side, flux information from the right hand side, and then this is value to here. So left hand side, right hand side that I need to say about here. We can interpolate it, calculate for the right hand side is from this cell center position to the right point, or this kind of here. So we have between this cell center value, this is we have a two value to come to here. So this is in this value or this value. So this is interpolation of the right direction or left direction. We are mixed up to this two information together to calculate for the Riemann problem to get in for the exact flux at the one interface. Okay, this is a bit complicated situation. Maybe you can understand. Okay, so this is a approximate Riemann solver. Here I can say about for the H-rail flux. So this is the several couple of the situation we can use in for this the approximate Riemann solver. This is the Lux-free Riemann solver is the most simplest version of the H-rail Riemann solver. And then the mostly we are using for the HLE approximate Riemann solver. This is using for the single state in the Riemann form. Or more higher order to above for the Riemann solver using for the HLC. We have a two state of the Riemann form to consider about for the contact discontinuity to here. So HLL is mixed up to this intermediate the region is only for the one flux. But HLC is also considered for the contact discontinuity. This is right hand side or left hand side, we can divide it. HLD is also again to including for to the alpha wave information also. Yeah.
What is the Riemann fan?
Riemann fan is okay. So this is we say this is.
We know that you are a Riemann fan.
Yeah.
But what is a Riemann fan?
Yeah, this is the characteristic information to inside to this what kind of the information right there. Yeah. So we say this is how much is the state including for to the within to the this two characteristic speed. So like this the fast speed like this if MHD case. So this is a fast magnetosonic wave inside only one state, or consider for the fast magnetosonic with the contact discontinuity, then we can get in for the two state. Or we also additionally consider for the alpha wave information to right hand side, left hand side, then we can divide 1, 2, 3, 4 information inside to this point.
So here in this example, you are considering one discontinuity
Yep.
and the characteristics that flow from it, right?
Yes.
So, okay. So what is the rarefaction wave?
Yes.
Is it that is
No, it's a rarefaction wave. Is everything is going to the right or left. This is so it means to the magnetohydro. We say this is to the fast magnetosonic wave or slow magnetic wave, or this is So we have the many the wave inside the MHD case, and then this is also each the wave is making for the shock or rarefaction wave. So sometimes this is fast magneton, fast shock, fast rarefaction. Sometimes slow shock, slow rarefaction. This is also combination of the.
What are the dotted lines and the dashed lines?
This is dash line. It's mean to the contact discontinuity.
Okay.
Dotted line is considered for the alpha waves. Yeah. Low is everything is considered about a little bit. This is a full wave decomposition Riemann solver. We say it here. This is low type. But low type is usually it's unstable, so we usually doesn't use it so much now. Okay. So the next is
more unstable in practice?
Sorry, one more again.
Why is rule
Yes.
configuration more unstable in practice?
I forgot to the why it's unstable. Yes. Yeah. Sorry, I don't remember to this one.
It's regarding to the numerical solution of the primitive variables, because since the whole is the most precise Riemann solver solution, you have some numerical fluctuations that could produce some negative values.
But the fact that we have everything in account, it means that we can the system can actually select the best, let's say the best characteristics in this sense. So in this sense, it might decrease the noise rather than.
Because of the precision of the. No, because the numerical fluctuations will be dumped by the most diffusive Riemann solver, if I understand. Yes.
That's
You have
true.
numerical fluctuation.
That's true.
too, because that
Why
you,
is that
but
the
you're
less
right,
diffusive? Why
it's
is
not
that?
the most diffusive.
Why
It's
is
the
that
most,
it's the less diffusive?
because
Yeah.
if I understood the whole, it's the exact solution of the Riemann-Solver problem because you are using the Jacobian matrix
Yeah, so you are taking into account all the,
Mhm.
let's say, all the
of the characteristic
yeah.
wave velocity of the system. But
Yeah, so
Yeah.
why is that?
understand as this way.
Yes, understand the law is a bit, yes, of course it's expensive, and then something is
Yeah, I can
sometimes,
understand that it's more expensive, but
yeah.
it should
That
be
yes. Yeah, of
more
course,
stable.
it compared to the HLD, it's CHLD is getting for the more, the, how to say, is a less diffusive structure. Yes, this is more, the more, yes, this is more,
The
less diffusive, because this is, we can consider for the additional wave information, then we can divide to the more, more, not averaging out of this information. So we can, exactly we can get in for some point, this information. Then the low type is everything we can mix up. So then we can get in for the more precisely structure, say. I think it's a smooth structure may be okay, but if say about some shock wave structure to happen, then the sharpness is broken up for the numerical instability usually. So at least my understanding, it's something mixed up for the sharpness and with the roots of the sharpness, like this, the diffusivity. It's keeping for the more stable to the calculation because everything's not perfect yet to the method.
So you have the sharpness.
Yeah.
You may have several peaks
Yes.
inside.
Yeah.
Makes sense.
So this is, yeah, mostly we are, why we are using for to the HLL, it's compared to HLLC or HLD, because this is more diffusive and then this is more stable to calculate for the longer time case. Then, okay, so the next is talk about for the constraint transport. Here we are talking about for the most of the hydrodynamic equation using for the finite differential method. We are think about for the how to solve it for the propagate of the wave to the next time step. But if consider for the MHD case, we are think about for the divergence B problem also including here. Yesterday I can say about for the this equation also including for the divergence B problem. The B is satisfied if using for the analytical calculation based on this equation. But this is numerically we have some noise inside to the simulation. Then this noise is numerically also numerical method it doesn't handling for to the this divergence B properly. Then we can increase for the divergence B problem. So here recently we are think about for the more clearly to how to handling for the divergence B problem into the numerically. So this is a differential equation including for the coupling for the divergence B. So we need this is divergence B is time derivative equal to 0. So this evolution of the equation can keep divergence free the magnetic field. If treat the induction equation as all other conserved equation, it cannot maintain the divergence free magnetic field in the numerically. So we need some special treatment for the magnetic field evolution to the separately with these hydrodynamic quantities. So now we have several techniques to consider about here. This is a constraint transport scheme. Constraint transport, it means that we can collection of some flux to the magnetic field to get in for the divergence field. This is divergence the free magnetic field structure. So first, it's proposed by the Evans and Horwitz. This is constraint transport scheme using for the staggered mesh point. Then also after that, the TOS it's proposed the flux the interpolated the constraint transport scheme. Then later, the Gardner and Stone also proposed the fixed flux CT or upwind flux CT, getting for the more higher order type of the flux constraint transport scheme. Then also we have a Balsara or some other Delzana also show about for the third order, fifth order, fourth order, like this higher order constraint transport scheme is proposed. So because this flux CT flux interpolated constraint transport, we are mostly using, but this is complete second order space. So we cannot get in for the higher order in this case. So we need consider about if getting for the higher order simulation code, we need some higher order constraint transfer P should be used. Other method is, we say this is diffusive cleaning case. This is, we say the GLM and the formation to there. We need additional function for the psi, and then this is making for the divergence beats happen. We can advect, and this is damping with the time to time. So this simulate this method, it doesn't should be getting for the same divergence beam number into the simulation, because we doesn't keeping for the divergence free system. But anyway, it's cleaning up this divergence field, magnetic field is with the time to time. This is one of the techniques to using for this. So this is a staggered constraint transport. So we're using for the staggered grid with the magnetic field is defined as the cell interface and evolving magnetic flux through to the cell interface using to the electric field is advected at the cell edge point there. This keeps the foreign to the cell-centered numerical representation of the divergence B is invalid. So this is a very simple way to using for the magnetic field. It's just consider about for the cell interface point rather than the cell center point. We can get in for divergence phi. It's automatically satisfied in this equation. But problem to the most of the fluid equation, fluid point, like this velocity, density, and also gas pressure, it's everything cell center point. Just only for the magnetic field, only for the cell interface point. But if you see about for the equation, we need energy or momentum equation. We need cell center point of the magnetic field. Anyway, we need some interpolate with this updated magnetic field into the cell center point. So this is additional technique or some additional ray configuration. But this is the most simplest way to get in for there. So the second part is this is flux interpolated constraint transport. So using for the modified flux, if that is such a linear combination of the normal flux that the neighbor as interface in the corner centered numerical representation of the divergence B is keep invalid during to the integration there. So this is we can get in for the one numerical flux point this value. So we are correction is coming from the 1, 2, 3, 4, 5, 6, 7. This surrounding for the neighbor point to get in for this one value to there. So exactly this is written for this kind of equation we can get in for here. Then this is automatically keeping for this divergence B problem. This is a 2D problem. Of course, now we can consider about 3D. We can think about for the additional surface. Each surface we can think about there. So this is okay. Yep.
So I noticed that all of the references you mentioned for the constraint transport are after 2000.
Yep.
So does this mean that MHD simulations before 2000 were not able to keep divergence free?
Yep.
So all of the MHD simulations before 2000 you can throw in the trash?
No, I don't want to say that.
We had
No, you can say. You can say.
no,
No.
he counts because he used as well. What
Yeah, actually, yeah.
Yosuke, I want your answer on the topic. What do you think?
Yeah, of course, the problem to that, yes, how much divergence B problems happened inside of this simulation. If this simulation is enough short time scale, divergence B is doesn't so much high number, like this 10 to minus 3 or 10 to minus 4, I think it's okay. But if this simulation is quite longer, so recently the most of the simulation becomes a very, very long time evolution. Then this kind of truncation error is every time contaminated, making for the divergence B problem. Then we doesn't trust about things.
Can I
Yep.
make a comment on
Yep.
this? Because of course I did a lot of numerical simulations, MADD numerical simulations before 2000, and what we used were exactly corrections step by step. So you had this divergence of B getting different from 0, but then you had a narrow condition to minimize it, and then you could clean step by step. Of course, it was something that it was homemade because it was cooking, but at the end you had results that you can still compare with nowadays simulations, present simulations, and they keep reproducing what we did in before 2000. So exactly the physics, the major physical points you still get in those numerical simulations, they're essentially correct, just that they are more noisy. So you do not have as many beautiful pictures out from the simulations as we get nowadays with the current precision of the methods, but the growth features are there. So
Yep.
I'm trying to understand what was
Yep.
the conceptual novelty of the constraint transport.
Okay, so the first is, of course, the Betty mentioned previously, before the constraint transport scheme is proposed, we are mostly using for the divergent cleaning method to handling for the divergence. Briefly.
Also the potential vector.
Potential, yes. This is vector potential way is also the another way.
Divergence of beats is strictly equal to
Yes.
zero.
Yeah.
So there were methods.
I have a doubt about this because since you can use the vector potential instead of the magnetic field, why to use the constraint transport? What are the advantages to use the constraint transport instead of the vector potential, for instance? Because the vector potential it's the the best way to keep the divergence.
Yeah, keep the divergence, yes. But initially, how to set up the magnetic field? Of course, it's a
The vector potential. The problem is that numerically, it's not always easy to solve this. It's more expensive to solve the vector potential. Yes, this is yes, it's
The vector
a long.
potential is it's expensive than
It's more
constraint
expensive.
transport.
Yeah.
So of course, yeah, we try to consider about for this kind of way. This is the more easiest way because here we just only talk about for the uniform grid case. But if think about the A-map case, it's how to divide in for the cell information to how to changing for this magnetic field or some other quantity to keep in for the divergence field problem. So this is every time it's coming for here. Then the most simplest solution is we are using for the divergence cleaning way. So this is a long term. But now we are also the new technique handling for the flux CT or staggered case. But yes.
Used to be less expensive
Yeah.
and useful for problems with some symmetry.
Yeah.
Right? And
but in general, is that vector potential is expensive, and then to get in for the how to initial set up the vector potential, this is a problem. After that, of course, is the calculate for the vector potential to get in for the what's the exact magnetic field structure. This is also numerically expensive to say. Okay. So this is yes. I think it's the answer to your question also, right? Okay, good.
Thank you.
No, it's okay. So this is talk about a little bit about the equation state. So now this is a bit out of these topics, but I try to say about for the general approximate equation state. Now we are handling for the sometimes here. In the theory for the relativistic perfect single gas, so this is specific enthalpy. Yes, it's found of the function of the temperature alone. This is the Cindy in 1957. So this is the function of the H. It's getting for this is the second order, the third order of the modified Bessel function with the theta. Theta is the temperature or P over rho function to get in for here. This is the exact here. So this is the constant gamma rho equation state. This is ideal equation state. It's using for this enthalpy is 1 plus gamma over gamma minus 1 as theta is a P over rho. Then this is gamma equals a constant specific heat ratio. But this is sometimes a problem for using for this constant gamma rho equation because relativistic case is a propagation to the light speed. It's a constraint of the c over square root 3. But if we are using for maybe we can see it here. This is a equation says gamma. This is 5/3 and 4/3. Maybe you know about for if this is the gas is less relativistic case, equation state is 5/3. But if gas becomes the relativistic temperature, we using for the 4/3 typically. Then between this values happen to there. So if this is just only about for the 5/3 is constantly, then getting for the very high temperature case, sound speed is going up to the 0.8c. This is exceed up to the c over square root 3 case. So sometimes this kind of situation is physically not correct one. So this is the types is the fundamental inequality to consider for the h minus the theta temperature. It's to getting for time to the h minus 4 theta. It's larger than to 1. Then after that, this one we can get in for to the equivalent equation, the adiabatic index. It's calculated for this one. So temperature going to the 0. So this is the equivalent. The adiabatic index is going to the 5/3, but this temperature going to increase at the infinity. This is going to the 4/3. So here we are getting for to the enthalpy to based on to this temperature function using for the Bessel function. We can exactly get in for the what adiabatic index in this temperature. But this the modified Bessel function is solving for the numerically. It's very, very expensive. So we need somehow we try to making for the approximation of this in this equation state. We are solving using for this kind of the function over there. So I think this is this is the equation state over there. This is the black line is this is Cindy's equation state, is the exact one. Then this is dotted, it's either equation state plus to the gamma equal 5/3, and then dashed one is either equation state plus gamma equals 4/3 one. Then dash dotted one is using for this TM equation state. I think we see to the doesn't so much difference between to this exact Cindy's equation state. So good point is this equation state is also keeping up to the root c over root 3 to get in for the maximum of the light speed is also keeping up here, and then smooth transition between to the 4/3 and the 5/3 between to there. Okay, so this is one of the approximation in the equation state. So to there. Okay, so this is the numerical test. So we have the various set of the numerical tests for the validate for the code accuracy and the performance. So that okay, I need to say about the previously I just already show about for the several steps of the high resolution shock capturing scheme. So high resolution shock capturing scheme is considered for this time updated using for the longitudinal method, then the spatial reconstruction and calculating for the numerical flux, then add to this is constraint transport scheme to handling for the diversity. This for the scheme is everything mixed together inside the high resolution shock capturing scheme. So this is the several tests is going to there. One is the famous wave propagation. It's also used for the comparison with the exact solution and check of the convergence. And shock tube test is also compared to the exact solution and check the convergence. And then so the magnetic loop advection is checking for the diversity problem, how to handle for this one. And a blast wave propagation without the magnetic field also we can see about sometimes. And then shock-shock interaction or Kelvin-Helmholtz instability. This is checking for the growth rate. Or jet propagation, magnetic reconnection. This is checking for the resistivity or additional test. So this is historically we are MHD simulation code. If you can develop a new one, we try to use them for the several numerical tests to passing through to this code is your valid, and you also checking for the what's the code accuracy or what's the code performance. Then after that we can apply for the actual problem. So good point is that we have so many reference to using to this kind of test. We have already the previous code has already passing through there, so we can do that.
In your opinion, what are the 3 most important tests? Of the list you put there, what are the top 3?
Top 3 shock tube test, and then to the magnetic loop advection test. After that, it's quite depend on the problem. So if
your list reconnection is at the bottom.
Yeah, because this is the resist. Yeah, yeah. No.
If you understand what we said is that there is no such an answer.
Yeah.
No, but this is very important because there is no such an which test is the most important one, because it always depends on the problem that you are studying. So if you are studying subsonic flow, of course you do not have to test shocks with your code, because you know if you are using a code that everybody else is using, it's a well-tested code, and this has been done. If you are testing resistivity, then magnetic resistivity, then the only way to see if your code is good or not is to do a reconnection test, but not with turbulence. You should start with a laminar flow, because if you use a turbulent flow, you are going to be how to say, you will not get the answer that you might expect, because turbulence induces by itself resistivity, natural physical resistivity, and it has nothing to do with the numerical resistivity, right? So you have to be careful. The problem that you deal with you will know in advance which is the best test to do. Right?
Yep. So this is based on this is up to here. This is the ideal MHD test usually. Then this is we can only add to the resistivity test here, because. Yep.
But how many of those do actually have specific analytic solutions? Because what I see is
Yep.
like lots of people do benchmarks that compare
That's
different
yes.
codes among themselves.
Yep.
But then if every single code is making some sort of rookie mistake,
Yep.
then you miss that.
Yep.
And I know, for example, the shock tube, we do have
Yep.
a solution. But for example, when I was trying to do self-gravity and
Yep.
incorporate it in Numerical, as far as I know, there aren't any real analytic solutions that you can test your code and see, oh, okay, my hydrodynamics is working perfectly. So I'm interested in doing magnetohydrodynamics.
Yep.
And I still don't have the magnetic bit. So what analytic benchmarks can you use
Okay.
to test?
Yep.
You
Usually
have
yes.
the Brio-Woosh shock problem?
No. Yes.
Right?
This yes.
Basically the shock tube.
Yeah. Shock tube have an exact
magnetic
solution. Yes.
fields, but other than that, which one would
Yeah, if you think about photo, yes, yeah, mostly the
Essentially, this one and wave propagation is very important.
yeah wave propagation is think about the alpha wave propagation like this. This is the exact solution we can get.
Reconnection is very important as well, because you do with the turbulence, MAGD turbulence. But you should, as I mentioned before,
Right.
you need
So-
to test
But then
this.
do you have an analytic solution that you're expecting out of this as well?
Yeah.
You do.
Okay.
So at this is mostly we can compare to the exact solution. Otherwise, mostly we can compare to the about the previous simulation code result.
Yeah.
Like this, we can follow to the same initial setup and the same grid resolution. Then we can get in for the same result or not. So this is most we can do in for that. So this is problem for the yes Newtonian case. It's more number up to the exact solution to compare to the GR case. Maybe Thursday I also talk about a little bit about for the what the numerical test relevant for the general relativistic MHD case also there. Okay, so this is code accuracy. Mostly this is I show about for my writing code. It's based on the previous 2006 test. So this is the 1D the alpha wave propagation test. This is just we know to the propagation initial setup, and then this is propagation passing through to the a few times through to the simulation. Then we can compare to the exact solution. Then if you see about for the how much difference we can get in for the L1 norm error of the magnetic field, or this is the y velocity. Oh no, yes, this is here to show about for the this is second order accuracy to here. So this is the number of the grid. The how much error is coming to here. Then you say this is Godon type scheme. It's allowed to get in for the convergence, to get in for the numerical code. If you get in for the smooth situation to there, so we can compare to the exact solution. Then we can get in for the L1 norm data. Then if you get in for the higher number of grid, we get in for the smaller error. Then if you see about this slope, we say this is not third order. My code is like this, a second order code. So this is mostly we think about what's the code accuracy. Let's say this is second order or third order or more higher. This is getting for the what's the error to compare the exact solution. Then we can calculate to changing for the different number of the grid with the same test. So this is the advection magnetic field test. This is a 2D. We can show about for the B square value. So this is the initial setup. Then we can, if it doesn't have any no advection, we can also keep in photo that nicely to this magnetic loop structure inside there. Then a second test we can just do it for the advection to this direction, and then this is the passing through to the one direction, and then we can return back to here. We can compare to this initial state. This is if this is mostly we can using for this kind to the propagation test to about for the magnetic field to checking for the divergence B problem is clearly doing for here. Of course, you see about for the some we are using for the flux CT scheme, but this is we can keep in for the this is center the circle region. It doesn't have any magnetic field line, but also the some small behavior to about for the some changing to the value, because this is still the flux CT is making for the divergence B its problem is clear, but how magnetic field is up the treatment is still this is second order level. So this is some small error is also coming from here to there. So higher order scheme is getting for the more nicely behavior to structure, but this is also depend on the code or the method. So this is the shock propagation in the high resolution shock capturing scheme case. This is a stable and accurate shock profile to making for the shock tube test, and then we can get in for the accurate of the propagation speed on the discontinuity, and then we can also accurate the numerical resolution, the nonlinear feature, discontinuity, refraction wave, vortex, and also turbulence into this high resolution shock capturing scheme. So this is the shock tube test we can show about here. So this is I think it's a show about the density. So this is the refraction wave, and then this is intermediate shock. This is shock wave, and then refraction wave to also propagate over there. So black lines show about for the exact solution, and then the other line is getting for the different the method, but this is a little bit mess up. So the different method have some different a little bit the future. Like this small oscillation sometimes show about for the higher resolution, higher order scheme, or like this the min mode structure, we say about a very diffuse structure to make of the shock position. So what kind of the method you can use, also you need once you can test then what kind of behavior you can show about for the shock structure, then you need to understand what your property of each code. So this is also the one of the cylindrical the explosion tests to including for the one direction magnetic field, so how much it propagates onto the this is I type of shape is made up to there, this case. Okay, so this is code accuracy. So this is simple shock tube test using for the one CPU to calculate for the one initial time. Then we can change in for the number of the grid. Then how much time you need to calculate to here. So
based on Racine.
This is based on the Racine code, yes. But this is a general, because delta t we say this is a simulation time scale. This is nx square, because this is a one-dimensional calculation. So if you increase for the number of the grid, getting for the same boundary position, we can get in for delta x becomes smaller. So if you're using for if you number of the grid become twice, we need to calculate for the twice time to get in for the number of the cell. But in this case, delta x becomes smaller. It means the delta t, it's become also the smaller half. So it means simulation time is getting for the square need to time. So we need to think about what this is only even for the one-dimensional case we can get in this kind of situation. If think about the two-dimensional, three-dimensional, how much you need to take the time to the higher resolution case, you can estimate. But this is only we can think about one CPU case. Of course, if you're making for the parallel case, we can get in for this number, it's less. But you need more number of the core to calculate. So this is my writing code also try to calculate the parallelized accuracy. This is a 1D shock tube test in the 3D Cartesian box. This is a fixed grid number of the size, and then calculate for the exact same time. Then using for the number of the CPU with the what's the speed up between to the initial time and to the number of the grid time. So at least we can get in for the 512 core I can use previously. Then this is the exact solution. No, this is the is the estimated accuracy of the 99%. I think my code is more than 99% of the parallel accuracy to get into there. I think this is better number. For me, first time I can try, I'm a little bit surprised I can for this number, but it's nice for me. So, okay, this is a summary. Okay. For there, this is finite difference scheme are the one of the common used for numerical method for solving for the partial differential equation, features based on to the discretized in the x and y plane with a mesh discrete point. The simplest linear hyperbolic equation is the advection equation, and the simplest nonlinear hyperbolic equation is the Berger's equation. The Berger's equation shows the shock steepening, which is consequence of the propagation speed is not being to the constant case. Riemann problem is the initial value problem with the discontinuous initial data. It's consistent rarefaction wave, shock wave, and the constant discontinuity. So high resolution shock absorption scheme is a higher order finite differential volume method solving for the conserved form of the partial differential equation, which approximates to the amount of numerical dissipation into the vicinity of the discontinuity. So mostly we are using for this kind of method to solving for the hydro and MHD equation. Okay, so this is finished to today's lecture.